Okay, it's about to get real on this vlogging with log video. I have to admit something to you. I lied to you. I lied about water. Remember when I put that light bulb in the distilled water and it didn't conduct electricity back in unit 3, I think, when we learned about compounds, and covalent compounds don't conduct electricity because they don't form ions? Water forms ions, you guys. So this changes everything. But first, because you watched the last video, remember how we would write water as HOH in our double replacement reactions? Is it an acid? Yes. Is it a base? Yes. It's both. But it behaves like an acid a little bit, in that water ionizes. And we talked about how acids react with water, and that's what ionizing is in the last video. Water also does that. Water reacts with water. OMG, watch this. So I can write the reaction H2O plus H2O, ionizing. So we need to form ions. One of the waters actually donates to this guy, to the other water, and giving us that hydronium, the H3O plus ion, and then the OH minus ion. This is the self-ionization of water. Now, I want you to think about how I put that light bulb a long time ago in the water and it did not conduct electricity. So is water strong or weak? There weren't enough ions in the water to make that light bulb light up. So water must be weak. So we throw a double-sided arrow here. And in your bottle of water, you mostly have water together. There's only a few of those ions kind of floating around. So it's never possible to have truly just pure water, because you'll always have those ions kind of forming. And even if you add acid to water, you'll still have some base, some OH ions forming. If I were to ask you, if we think of last unit where we wrote the equilibrium expression for this, I'm going to write states of matter. This is aqueous, this is aqueous, this guy's liquid, this guy's liquid. We don't include pure liquids or liquids in our K expression. We would write that K is the molarity of, I'm going to write H plus instead of H3O plus. Just letting you know, I'm too lazy. Molarity of the H plus, so there's my bracket for it, times the molarity of the OH minus. And K, we know that it lies mostly on the reactant side, so I would say in class, hey, would we have more reactants or more products? You have more reactants. K is going to be a really tiny number. It's temperature dependent, but at 25 degrees Celsius, K is equal to 1.00 times 10 to the negative 14. So do you see how tiny that is? In your bottle of water, you got mostly the H2O stuck together. So here, if I just kind of take the K out, is a new equation we can use to find molarities of any type of solution, whether it's acidic or basic. This guy. And in class, I'd be like, write this on your note card. It's really small. If we could try some problems, knowing that the KW, we're throwing W in for water, is 1.0 times 10 to the negative 14, we can solve for these two concentrations. So if we've got kind of our like pure water solution sitting here, if I plugged an X in, what's awesome is that the H's and the OH's, since one water molecule kind of split apart to make them, are always equal. So we can throw an X in for both of those. So essentially X squared is equal to this. And then to solve for it, I'm going to do the square root of that. Root. The molarities end up being 1.00 times 10 to the negative 7, so really tiny. So if you've got a glass of ice water in front of you, there's hardly any H's and OH minuses in it. But we can trip it up. And tomorrow we'll talk about the pH scale and how it's based off of those. But with an Arrhenius acid, if I add HCl to the reaction, we're really adding H's and we're adding Cl minus ions. All right, I'm gonna ions to the solution. So this guy is gonna go up. The OH minus amount will go down because K is a constant and it stays the same. So I'm kind of goofing up. I didn't really mean to do that slide now that I just said that. So let's try a problem. I'm gonna give us, here's our equation. 1.00 times 10 to the negative 14 equals this guy times this guy, the H plus and the OH minus. I am placing 0.100 moles of HCl in 1 liter of water. So the molarity of this is 0.1 of HCl. And HCl is a strong acid. So that means that all of it ionizes. So if I have 0.1 moles of HCl, I'm going to make 0.1 moles of H plus. So we already know that first answer. The H plus concentration is 0.100. But I want to know the OH minus concentration. So all I need to do is I just plug that concentration into the equation up there. So I would do 1.00 times 10 to the negative 14 equals 0.100 times OH minus, like its molarity. Oh, my stylus is dying. I don't know what that means. And then to get the OH minus by itself, I am going to divide by 0.100. And we end up solving that when I do that math, I get 1.00, I think it's times 10 to the negative 13. Really tiny. So that OH minus concentration, even though I put hydrochloric acid in the water, will never be 0 because water self-ionizes and there'll always be a little bit of OH minus present, but it's super small. We can do the same thing for bases. If I have a 0.010 mole solution of sodium hydroxide is strong. It's an ionic compound and it completely dissociates when we put it in water. The OH minus concentration, we know that for sure, is just that number, 0.010 molar solution. That's asking for the H plus concentration. Here's our equation. 1.00 times 10 to the negative 14 equals the molarity of the H plus times the OH minus concentration. I'm just going to throw that in because I'm just going to. And then I'm going to divide by that to get it by itself. We get that the H plus concentration, oh my gosh, can I math this? Is 1.00 times 10, is it the negative 12? I love that I'm looking at my camera screen, like waiting for one of you with a calculator to answer me. So even though I put sodium hydroxide in water, because water is present and water can act like an acid and a base, there will still be the other ions present. So I just want that to be clear. Water self-ionizes. Overall, though, the H's and the OH minuses are equal if it's completely neutral. So my mentioning here, we'll talk a lot more about it because water makes an H the acid and an OH minus. It's considered to be neutral, and as you'll see to calculate, the pH is always 7. So water, I lied to you, I'm sorry. So, okay. Actually, I don't really feel bad, but